So hello and a very good morning to everyone, and a very good afternoon to those who are seeing this video after 12 p.m. So today we are going to start with our first chapter of air navigation series, which is the solar system. In this, we are going to start with the Kepler's laws, followed by seasonal variations, after which we will see types of days, types of years, and in the end, the twilight period. So let's quickly begin with the Kepler's laws. So what did Mr. Kepler say? So he derived three laws which governs the motion of planets in orbits around the sun. So what are the three laws? First, he said planets revolve around the sun in elliptical orbits, of which sun is present at one of its foci. Then the second point, he said that the line vector joining the sun to the planets covers equal areas in equal interval of time. This means that the velocity of the planet is not constant. It's variable depending upon its position. The third law he gave, the law of harmonics, in which he said the square of the orbital period of the planets is proportional to the cube of the distance between the planet and the sun. But we are not going to just read it 5 times and try to remember it so that we could recall it during the exams. No, we are going to do an experiment in which we will actually take two foci and a string to draw an actual elliptical orbit. Let me show you. So we are going to use these as the foci. We are going to stick it on the board and we are going to actually draw an ellipse to see how, in which paths the planets rotate around the sun. And from that experiment, we are going to remember all the three laws in a way that we are never going to forget. So quickly note it down, then we could proceed to the experiment. So now let's erase it so we could proceed to the actual experiment. So we'll use this as our foci to draw an actual ellipse. So let's stick it. Now we'll take a string. This is the string, I hope you can see it. And using a normal marker, we will draw an ellipse now. So this is the ellipse, a perfect ellipse drawn using two foci. And why is this an ellipse? What proof we have that we could call this an ellipse? So the rule of the ellipse is any point on the ellipse should be the sum, adding the line vectors joining the two foci to the point. The sum of the length of these lines remain constant, and that's why to achieve that we use the string. So wherever we take the string, the sum would remain constant. So now let's understand the three laws Mr. Kepler gave us using this. First law, planets revolve around the sun in elliptical orbits and sun present at one of its foci. But here are two foci, so let's just remove one of them. Yeah, it's possible you can ask now that why I removed this foci, why not this? So the answer is simple, that no matter which one I would have removed, the entire thing would have been same. Just the things that I'm writing on this side, the data would have just been written on that side. So that's the entire difference. It does not matter which foci are we removing. Also, there may be a doubt that We are using two foci to draw the elliptical orbit, but there is one sun only. Why isn't there two suns too? Just like we use two foci. So the reason is the reason because Earth or any other planet rotates around the sun in elliptical orbit is not because it's connected to two foci. It's just because of gravitation. And let me write down the law, which is F equals to G M M by R square. So this is the reason why the planets rotate around the sun in elliptical orbits. The gravitational pull. It does not rotate in elliptical orbits because it's connected to two foci. So I hope you understand that. The second law Kepler gave, that the line vector joining the sun and the planet sweeps equal areas in equal time intervals. So again, let's draw it out first. So let's say first the planet is here, then here. So let's assume it took 10 days for planet to come from the upper position to the lower position. So what is the area covered by this? Let's draw it out. This is the area. Similarly, the law says it always covers equal areas in a given interval of time. So if we draw it on another side, let's say this. Let's erase the extra things. Now let's join it. This is the area. Now, you must have noticed one thing. This, the distance covered in 10 days, it seems much larger than that. Why is it so? Because the law says the area covered should be equal for a given interval of time, that's 10 days. So if we increase the distance here also, like it's that side, the area would increase drastically because the area of a triangle is half into base into height. Let's first write it down. According to this area, the base is larger and the height is something, let's say 5 and 5. Now here we can see the height is drastically increasing. This is the height, probably 10, whatever unit you may want to fix. So if we keep the width equal, that's 5, both of these values would not be equal anymore. This proves the fact that the width here needs to be lesser so that the area covered remains equal. Now if we see half into base into height and half into base into height, now these are going to be equal. So from this, Mr. Kepler gave the final conclusion that this law proves that the velocity of the planets in the orbit is not constant. And that's why in the time interval of 10 days, the distance covered varied. This is the second law that Mr. Kepler gave. Now we'll come to the third law. T square equals to R cube. This. No, now as we explained that the square of the orbital period is proportional to the cube of the radius, basically the distance between Sun and the planet, is proportional. Just a second. Yeah. So, what does this actually mean? It means that the planets that are closer to Sun, whose radius is lesser, they will complete their orbits quickly. So are we going to just believe it because I said it? No, I will give you an actual real life example. Mercury, the planet which is closest to Sun, has an orbital period of 88 days. What does this mean? While Earth takes 365 days and 6 hours approximately to complete one revolution, Mercury only takes 88 days and it's done with one revolution. One more, the planet Neptune, the farthest planet in our solar system from the Sun. Neptune takes 165 years to complete that orbit. 165 years just for one orbit that we take 1 year for. This is the difference. Let me write for the Mercury too. It's just for extra information. It is not something that you need to remember for exams, just so that you could understand this law. So we could, if we want to say in brief, we could say, if we are going to increase the distance between the Sun and the planet, the orbital time, the time of one revolution around the Sun, will also increase with this. This is the actual understanding of the three laws Mr. Kepler gave us. Now, I hope you could note it down so we can proceed to the seasonal variation after this. So, note it down. Let's proceed. You're going to leave the ellipse on its place. Yeah. So now we are going to start with the next topic, seasonal variations. We'll first draw it out on the board, like where is Earth present in what season, and then we'll understand it, all the important terms that are given in it. So while earlier studying this, I found an quite easy way to remember the dates that are given to the season. So in this, we start with the rule of 1, 2, 3 for months. So just see it, how do I do it, and then you can remember it. You just need to remember December, add 1, January, add 2, we'll get March. Now add 3, April, May, June. Repeat it again, add 1, we'll get July. Add 2, we'll get September. And just for confirmation, you could add 3, you'll get December only. That's already written. For date, on which exact date this happens, you could remember 3 on opposite sides. Start with 21 here. Repeat it. Add 1, you will get 22. And again add 1, you will get 23. So these are the dates. You can remember it in your own way. You don't need to follow this, but the dates will remain same. That's 22 December, 3rd January, then 21st March, 21st June, 3rd of July, September 23rd, and again December 22nd. Now let's understand what are the meaning of these perihelion, aphelion. What are these? So starting with perihelion, there's one trick my teacher taught me, that relate peri with pass. So perihelion, Earth is closer to the sun, Earth pass mein hai sun ke. So this is the point where Earth is closest to sun in terms of distance. Opposite of it, aphelion. Earth is farthest from the sun distance wise. Then autumn equinox and spring equinox. These are the dates when the duration of day and night remains exactly equal. Here in spring equinox and here in autumn equinox. Whereas in perihelion and in aphelion, the duration of day may vary, the duration of night may vary in northern and southern hemisphere, but at these two dates, September 23rd and 21st March, in both northern and southern hemisphere, the duration of day and night will be equal. Let me show you with a globe to understand better. We have a globe here, and you notice it's tilted to an angle. It's not because you can see it in a better way, it's because Earth is actually tilted like this in its orbit by 23.5 degrees. If you sometime get time to read the value written here, you'll notice it's somewhere between 66.5. Why? Subtract 23.5 from 90, you'll get 66.5. That's what's done in the actual representation too. Now let's understand. Spring equinox, autumn equinox. I said the duration of day and night in both northern and southern hemisphere remain the same. What does it mean? The sun is exactly in the middle. If the sun was above, let's say above northern hemisphere, the northern hemisphere would have got a higher duration of day, as happens in summers. If it was in somewhere around the south, the southern hemisphere would have gotten more part of the day, as happens in winter for us, and it's summer for the people living in southern hemisphere. That's how it happens. So in equinox, whether it be spring equinox or autumn equinox, sun is exactly in the middle over the equator. Get these two things? Then winter solstice and summer solstice. So for us people living in India, this works correct, because let's start with summer solstice. Date 21 June. What happens in this? The sun is on its topmost position, as high it can go. Just let me mention, sun cannot go up to the North Pole. Above from equator, there is a certain latitude only up to which the sun can reach. That's 23.5 degree. Tropic of Cancer. That's definitely something you must have heard. So that's the point. The sun is above Tropic of Cancer in summer solstice. It's summer season for us. Date 21 June. Winter solstice, obvious, winter season for us. Duration of days are lower. So where would the sun be? Somewhere around the southern hemisphere, above the Tropic of Capricorn. That's the latitude of it is 23.5 degrees south. This is how to understand winter solstice and summer solstice. The name, you could remember it using in winter solstice, it's winter season for us, December months. In summer solstice, it's summer season for us Indians, 21 June. So like that, you could remember it. And if you would have seen the introduction, you would also remember how the earth is tilted like this. Let me place it here. So let's imagine the sun, which is present here. Let's imagine it to come out of board and stay here. Now imagine the sun here. This is our earth and this is the December months. You see how it's tilted like this? Here it's the sun, my fist is the sun. All the rays would be pointed in the southern hemisphere, let's say Australia, the lower parts of Africa, South America, Africa. So it is summer season, but for them, not for us. We are in the upper part. We are living here. Sun is pointing to the lower part, the southern hemisphere. It's winter season for us. The earth is rotating from west to east. So sun rises from east to west like this. Now this rotated, and it reached the opposite side. I hope you can see it. Reached the opposite side. Now you see the earth is tilted this side. Sun is here. All the rays are pointing to the northern hemisphere like this. And it becomes the summer season for us now. The winter season for the people living in southern hemisphere. So doing all of this in this imaginations, this would be the December January months like this, winter season for us. And after rotating like this, coming to the opposite side, this would be the summer season for us, approximately 21 June. I hope you can imagine it. So this is how the tilt of the earth causes all of the seasons, summer, winter, spring, autumn. So this is how it happens. So you could note it down quickly, then we could proceed to the next topics. So I hope you have noted it down, and this video is getting quite longer, nearing 30 minutes. So I'm thinking I'll shift the next 3 topics in the next video. I'll make a part 2 of this. In that we will cover types of days, types of years, and in the end the twilight period. So see you. Jai Hind.